Hi, in the previous videos, we talked about order of growth. We discussed different mathematical examples and explanations for order of growth. Let us now take more complex programming examples to understand different cases of algorithms. As a first example, I have taken a very simple code which does not have any cases. We'll extend this code so that it's going to have many cases like worst case, best case, and average case. Let's take a look at this code, and please pause this video and try to think of order of growth of this function. Order of growth for this function is clearly n, right? It's linear. You can see that there is some work which is happening linear time, c1n, and there is some work which is happening constant time, like these two, and initialization, all these things happen constant time, and there is this thing and this I++ which happens linear time, right? So c1n plus c2 is the time taken by this function, and if we ignore the lower order terms and ignore the leading constants, we say that n is the order of growth. We just figured out simple order of growth for a simple function. I have made the function slightly complex now. Say due to some business reasons, we want to return 0 when there are odd elements in the array, and otherwise we want to find the sum of elements in the array and return the sum in this function. Now what do you say about order of growth? We cannot say any particular thing about order of growth now, because in some cases when n is odd, it's going to take constant time, and when n is even, it's going to take linear time, right? So when n is odd, it's going to go into this condition and return 0, which is a constant work, and when n is even, it's going to run this loop and find the sum. So there are multiple cases now. We categorize these cases into 3 cases. One is called best case, one is called average case, and one is called worst case. Let's talk about best case time complexity or best case order of growth for this particular function. What will happen in the best case? In best case, n will be odd and it will take constant time. So order of growth for best case is constant. Let's now talk about average case. See, average case is something which is many times impractical to guess. You have written this function, you do not know how your users are going to use it. How are they going to provide input, and which input is going to be with what frequency? So if we know all possible inputs, we can say I'll find the order of growth for every input, do the sum of all order of growths, and then do an average and find the average order of growth. So in this case, if you consider even and odd equally likely, then you can say average case is linear, because for even it's linear, for odd it's constant, constant plus linear is again linear. You can see it as n by 2, right? So average case is linear under the assumption that even and odd are equally likely. So that's the average case. Now worst case. What is the worst case time complexity of this function? In worst case, your n will be even. When n is even, it's always going to take linear time. Doesn't matter. So worst case for this algorithm is, or this code is, linear. That's the order of growth of this function for 3 different cases. In general, when you analyze algorithms, you do not care about best case. It's considered as bogus. The reason is simple. If you build a software and you tell somebody that my software in best case takes 0.001 microseconds, or constant in terms of input size, I do not know about the worst case. It might take hours. So nobody is going to purchase that software, right? So worst case, best case is something we generally do not use. Average case, we would like to know. We would like to know how much is the average time taken by the software. but it's impractical to do most of the time. Also, even if you have data, it's too much mathematical for computer people to figure out sum and do average. Worst case is something which is we do most of the time. We try to find out what is the case for which our algorithm is going to take maximum time, and we find that time and say that worst case time complexity of this algorithm is order of growth in worst case for this algorithm is so and so. Please note that we make this decision of worst case only when we have different cases. When we have one simple algorithm that always takes linear time like the previous program without this condition, we can simply say that order of growth of this algorithm is linear, right? We do not have to mention any particular case. There are examples of algorithms which always have same order of growth in all cases. Merge sort is an example. This sum is an example. Minimum of an array is an example. Maximum of an array is an example. You will have to traverse through the whole array to find the minimum and maximum also. Let us now talk about mathematical notations required to represent order of growth. These three are main mathematical notations. There are more, but these three are the most used. And among these three, big O notation is the most used one. These notations are used to represent order of growth of a function. And this function generally represents the time taken by your algorithm. Same functions can also be used to represent space taken by your algorithm. So there are mainly three notations: big O notation, theta notation, and omega notation. Theta notation, the second one, this is used to represent exact order of growth. For example, the first code that we wrote, where we did not have any if condition, we knew exactly what is the order of growth of this algorithm in all cases. So we can put that order of growth in theta, and we say order of growth is theta n. Big O notation is used to represent exact or upper bound. We can put either exact value if we know it, or if we do know an upper bound, we can put an upper bound. I'll talk about this notation in detail in a separate video. Omega notation is opposite of big O notation. It is used to represent exact or lower bound on order of growth of an algorithm.